and selenite standard is the orange line. The major difference is there is a high peak in the selenite 10 millivolt sample for normalized absorptions. And also you can see there is an energy shift prior to that peak and another energy shift after the secondary peak somewhere here. So that might suggest a speciation change.
Okay, so now here is the Zane's graph for selenite. Similar to selenite, we eliminate the two possibilities of selenite samples being selenium sulfide and selenium oxide, because you can see the blue line is selenium oxide and the orange one is selenium sulfide. And compare these two to our selenite sample, the second one from the top here. The positions are very different, and in general the shapes of the peaks are also different. So we suggest there might be a speciation change between these two. So here we're gonna take a closer look at the selenite sample in our selenite standard, sodium selenite. You can see the difference apparently. The positions according to x-axis is different, so we see there was an energy shift, and the peak here is higher than the one in the standard, according to the y-axis normalized absorbance. So here we suggest there actually is speciation change, and a new compound has been formed.
I'm also going to talk about our analyzation for mercury, and keep that in mind, it's L-shell. I'm first looking at the mercury oxide, that's the blue line, and mercury chloride, that is the yellow line. In comparison to the two proprietary polymer, the mercury, you can see clearly there's a decline after the first peak, not the major peak, after first peak somewhere here and here. That didn't appear in our polymer. So we first eliminate those two as our possible compound that formed in the polymer. Mercury sulfur black and mercury sulfur red, they're very similar but also different. That is, there is a curve in mercury sulfide black here, while there didn't seem to be a curve in mercury sulfide red. And to be sure, we made an overlap graph for our polymer and mercury sulfide black. Here, the yellow line is our proprietary polymer with mercury, and blue line is mercury sulfide black. The major difference here, as you can see, the prepared polymer curved here, and it's not aligned with mercury sulfide black. Also, there's an energy shift after the major peak as it declines. That suggests there might be a speciation change in mercury, but it could possibly be that there's another compound, the polymer is impure.
So up to now, we don't have an answer to what the compounds are, but from our results, both mercury and selenium have likely bonded to the patent-pending polymer, respectively. And the products are not the standards we scanned, but so we suppose that could be something else, or the combination of the standards we have. Then, even though we don't know what a reaction yields to, but what we do know is there has been a reaction, which leads to the conclusion that that could be used as a future method to extract mercury and selenium from the environment, solving the current pollution problems caused by the uranium mining in Saskatchewan, Canada, or even in the world. And what is also possible and exciting is, besides sodium selenide and sodium selenate, other toxic selenium compounds could possibly bond to the patent pending polymer as well, since sulfur binds well with selenium. That leads to our future research.
For our future research, we would like to run an EXAF, or what we call the Extended X-ray Absorption Fine Structure Test. So what it is, it's a test that detects the bonds of selenium. Secondly, we would also like to run or relate to the application of the word. For instance, look for effects of polymer on the terrestrial environment, such as extracting heavy metal pollutants from the soil, which could possibly play a very significant role to Saskatchewan agriculture industry. Also, we would also want to look for other compounds that could create a similar polymer with different effects. And lastly, we would want to look for. We would want to make a procedure that can use to remove selenium from uranium mining.
So we've had a really exciting, amazing experience working with Canadian Light Source throughout the cooperation with CLS scientists and Dr. Justin Chalker from Flinders University. We gain unique and practical knowledge throughout these activities, and it also has taken our understanding of science to a whole new level, and and also it's been really exciting. We get to know about synchrotron and use it to help us solve the project. It's been really good.
So we would like to thank the Canadian Light Source for giving us this opportunity to experience research at the synchrotron. Thanks also to Dr. David Muir, Dr. Robert Blythe, Dr. Gosha Corbus, Miss Anna Maria Beckler, and Miss Tracy Walker from the Canadian Light Source for their mentorship and guidance. Another huge thanks goes to Dr. Justin Chalker of Flinders University for his collaboration, as well as sharing his materials for this project. A special thanks goes to the EHCI Synchrotron supervisors, Ms. Tina Ryu and Mr. Jason Kimberly, for their time and support. And thank you all for coming and listening to our presentation.
Does anyone have any more questions about our project?
So I know that there are some more materials that were available to you that you did not use, but I don't know if you specifically talked about that in your future research. Are you hoping or planning to test the other polymer that you have access to?
The other polymer, one downside to it is it has an extremely strong smell. So
Sulfur, right?
So that was one of the reasons that we chose not to work with it with selenium. That could be another potential path to go down to see if we could do something to lessen the smell and thus be able to work with it. But for now, we didn't have that in mind.
You showed a picture where previously it had been shown that only mercury caused the color change. But you're seeing that selenium also reacts. So did that other study also detect check whether selenium was reacting?
With our study, we checked to see if it was reacting. Because there wasn't a color change, it wasn't evident after we had done the procedure. So after more tests, we may be able to determine more if there was a bond.
And see if we can have a concrete result instead of just hypothesis.
But Dr. Justin Chocolate did not test selenium on his pneumonia beds.
Okay. Okay. That wasn't on that list.
If you were to put your polymer into a real world sample, what do you expect it to absorb?
We expect it to absorb mercury in small gold mining, since they're using mercury to combine with gold and then burning it to vaporize the mercury. We were hoping a real life example could be use this polymer to make a filter that you can replace after a certain period, after it absorbed to its maximum. But this is just a thought, like a real practical object or solution is not made yet. Same as selenium. Say in mining, it's all selenium or some of the selenium goes into a water lake. How we are going to clean up that? So we can make some kind of powder in a bag that will slowly absorb the selenium, and once we can replace it and find a way to dispose it safely.
And because these polymers were made with a high sulfur content, they are purposely made like that so that they can bind to things that easily bind to sulfur, like metals. So it could have the potential ability to remove other metals that we haven't looked into yet.
Right, that's my question. So you put it into a natural sample, how do you even know you will absorb selenium? All those sites might be occupied by the other metals.
Well, that is
in your future test. You need tell me what you're going to do in your future test.
That's what we're going to do in the future test, to test out if there's multiple elements or metals in the solution. If we can extract, if we would extract both of them, or if we would only extract one of them, and we're going to plan a controlled experiment.
You mentioned that you learned a lot about science and compared to what you learned perhaps in your classes. Can you be a bit more specific? How do you view science now differently compared to before you had this degree?
Well, I can speak, I'm in grade 12 now, so I've been through many science classes, and never have I had the hands-on ability to make our own experiment and then be able to use the synchrotron. Like, it was amazing to be able to go through the entire research and the process. It was just really enriching, and you never get that in a classroom setting.
Also,
come on now, easy.
And also about all the energy absorbance. That's what we didn't learn that in our high school. We don't know how you're going to test out what element is in the compound by using synchrotron, and we see all the X-ray spectroscopy. We can see all the energy absorbs level, and it's more a combination of different science, not just physics, not just chemistry or biology.
So I think that this opportunity gives us to learn that science is an interdisciplinary thing. It's not like only science class, only chemistry class, physics class, or biology class. They're all separate in the classroom setting. And here we have those knowledge that we haven't learned in the classroom. So we know science knowledge is way beyond our reach, and we are learning, and the learning is infinite. It's not only about scores or exams. What we are learning is the things we want to pursue. We want to know in the real world, and then solve problems in the real world.
Miss, were you our biology teacher over here?
Yeah.
Yes, and a lot about the selenium we learned in grade 11, and I think it was very interesting that how we were able to apply those knowledge that we had from our school into this presentation over here and overall in our general project. And not a lot of students our age get to experience such an in-depth study into these fields, and like everyone can basically back me up on this. Like this has been the most amazing experience for all of us here, like in our lives.
So we really appreciate that Synchrotron Canadian Light Source give us the opportunity to use and experience how the synchrotron works, and maybe that could be the only times in our life get to use synchrotron. So we really appreciate that you offered us this opportunity.
And on that note, on behalf of the Synchrotron Club.
No, there's more questions. I want to hear from the other students that haven't answered that question yet.
For me personally, also with Kayla, like I'm in grade 12, and sometimes when you sit in the class, all you learn is facts. You write notes down about, oh, this is selenium, this is what it does, but like actually getting to experience it, seeing how an actual procedure works, how an actual like experiment works, it's so much different because it's more hands-on and you actually understand it more. It like actually brings an interest to you. And this kind of prevents, like it helps us understand if this is something that we're interested in doing. Some of the people here do this like this is their job. They come every day and they like enjoy, like I know for Gosha, mercury is a big thing and she loves learning about mercury. But when you just learn the facts, it's not the same as when you actually get to work with it and see the results of it and see how it actually is gonna benefit, like how it would change the world or how it would change different like outcomes and like things that are happening. So I feel like for me, it was just the hands-on was so much more enlightening and so much more interesting for me than it is to sit in the classroom and just write notes about it, you know?
And also not just like learning knowledge about science, we also got to witness what happened. So it's a tremendous opportunity just to look at it and work on it. And I'm excited for next year because I'm in grade 11. Hopefully I can work again here next year. So I'm looking forward for it.
For me, I think working in a lab is a new experience that I never done before. It's really interesting to like deal with toxic material that you will never see in a high school classroom.
They never touch mercury.
It's clear.
So for me, it's like I actually understand like how hard the actual science is, like harder than what we learn, what we do at school. Like scientists actually spend like most of the time in the lab. Like actually, we spend like 8 hours in the beam line. It's really long. It makes us really tired.
Scientists spend much more, longer time on experiments. Yeah,
that's hard. So also I realized like which part like we should improve ourselves in order to like become a scientist in the future. That's what I learned.
And maybe not exact like definitely being a scientist, but process of this critical thinking that really will help us in different fields, not just in science research.
No, Melody didn't speak yet.
Oh, and this also goes to like the synchrotron being like such an advanced technology, and then this can be like a once-in-a-lifetime opportunity for like even some scientists, and it is like pretty amazing how we can work on a level of a project that could kind of be equal as some scientists, and it's just been like an amazing experience in comparison to school. Like with all the lab experience and then the focus on developing your own projects and like the success in receiving our results.
The classroom's really not that bad.
Sorry for not having a synchrotron.
Any other questions?
On the budget.
Are there any more questions? Okay,
No.
so now we would like to present a few gifts to some of our mentors because we know that they didn't have to do this, and it means a lot to all of us that they did. So this one's for you. Thank you guys. And then the card. Thank you.
You have to open them.
Oh,
Yeah.
I'm on the camera actually.
You are on the camera.
Oh, I was hoping to get one. I was hoping I can wear it actually. If you have one for me, I could wear it for the seminar.
support.
Not Queen Bee.
No, you can wear that one. This is regular
Oh
day.
yeah, I'm wearing it's like every day.
Yay!
Like it says core bus.
Thank you.
That's awesome.
Hey.